Good day, everyone. We are Group Binary Baldness. My name is Do Yujun.
My name is Ji Jun Yao.
My name is Daniel.
And today we are going to introduce you guys about our door control system.
So the aim of our door control system is to manage access, enhance convenience, and ensure safety.
So now let's dive into the details of our door control system.
I'm going to explain the general circuit of a door control system using this block diagram. A door control system consists of three inputs, which is the MO, motion detected outside, and motion detected inside, and also the lock state, the current lock state of the door. The two outputs of our door control system will be the door control, whether the door will open or not, and also the alarm system, whether the alarm will ring or not. When MO and MI shows high input, it means that either motion is detected inside or outside of the house, and if the lock state shows a high input, it means that the lock state is currently locked. So this is our truth table, and I'm going to show a specific example. When there's motion detected outside and there's motion detected inside, if the lock is currently open, the door will open and the alarm will not ring because this indicates safety for the owner inside the house.
Now we're going to show you guys how I create my logic circuit for this door control system. So first of all, we're going to have our truth tables, and so from the truth table we can derive our K-map. This is very important because by looping the value in K-map, we can get our simplest Boolean expression. For example, I looped all the values of 1 in K-maps, so I can get my simplest SOP form of Boolean expression for my first output, which is do or do. Okay, so this is what we get after I loop the K-map, which is MO bar and MI, or MO and LS bar. Okay, so now let's take a look at our logic circuit. This step now is very simple because I just convert the Boolean expression into the logic circuit. Okay, so this is MO, this is MI, this is LS input. So MO will go through the NOT gate and arrive at the AND gate, and then another MI will arrive at the AND gate. So the MO bar will go through an AND gate with MI, and then at the second part, the LS will go through the NOT gate and it will go through the AND gate with the MI, and eventually these two will go through the OR gate together and perform our first output, which is DO. Yeah. Okay. So now let's take a look at our second output. This is the K-map for our second output, which after we loop all the one value, we get our simplest SOP form as usual, which is AR equals to MO and LS. And this is pretty simple. When we take a look in our logic circuit, it will be like MO and LS, and perform our second output AR. Yeah. That is the end for the basic logic circuit. And now let's take a look at our NAND configurations. So for NAND configuration, I will just add double bar for each Boolean expressions, which in the first case, it will be like this. Yeah. And now let's take a look at our logic circuit. So it will be like, at the first part, the MO will go through the NAND gate within itself. This is to replace the NOT gate, okay? And then it will meet with MI at the second NAND gate, okay? And this is the end for the first part. And then for the second part, the LS will go through the NAND gate within itself. So the reason is still the same because to replace the NOT gate. And it will be go through the NAND gate, the second NAND gate with the MO, okay? And then these two, the result from these two gates will perform the output for DO, yeah, DO, okay? And then for second output NAND configuration, it will just simply be like double bar MO LS, and this is pretty simple. You just we get the input MO from here and LS from here, and then we go through the NAND gate again to invert it again. Yeah, it will be our second output for NAND configurations, and that's the end of the introduction for logic circuits.
Okay, so now I'm going to explain the waveform result for our basic logic circuit. I'm going to use this as an example. When MO is showing a high input and MI is showing a high input, if the lock state is currently showing a low input, the door will open and the alarm will not ring. So this result is compatible to our truth table and they show the same result.
As observed, the NAND logic circuit output matches the truth table and standard logic gates, confirming its accuracy. However, they differ in complexity, cost, and maintenance. The basic circuit uses various gates, which is more complex. In contrast, the NAND circuit only uses NAND gates, making it cheaper, easier to maintain, and more reliable. For the AR output, the basic logic circuit uses fewer gates, one AND gate, so it's faster, whereas the NAND logic circuit uses more gates, two NAND gates. NAND is slightly slower, but more cost-effective and simpler to maintain. The choice depends on the priorities of cost, speed, and ease of maintenance. In conclusion, our project boosts convenience and security with a compact door control system, featuring alarms and motion sensors that surpass traditional locks. Its more design ensures ease installation, maintenance, safety, and adaptability. As technology advances, our system becomes essential for homes and business, offering significant market potential by creating secure, convenience, and efficient environment for modern interconnection space.